Let's compute some flux integrals. So in this case, we have a vector field zx1, and we want to find the flux of this vector field through the unit hemisphere, and the orientation should be pointing upward. So to compute the flux through a surface, we want to parameterize the surface to the specified orientation and then set up the appropriate surface integral. So if I want to parameterize a sphere of any sort, spherical coordinates gives me a good way to do that. I just need to make sure that the resulting parameterization is pointing in the right direction. So what I mean by spherical coordinates is the unit sphere is given by rho equals 1, and so phi and theta could be taken as the parameters. So I'm writing u and v instead of phi and theta, but this is a parameterization of the sphere of radius 1. I'm going to go ahead and cut off the parameters so that I just get the northern hemisphere. Okay, so now let's inspect to see if this parameterization gets the normal pointing in the right direction. And I know a trick for reversing the normal in case it's not pointing in the right direction. I'll just completely reverse the roles of u and v in the expression. So if I come over to the picture, I had to imagine, like, how does increasing the parameter u look on the surface? So like if I'm at a point right here, and I increase the u value, which is acting like the phi in spherical coordinates, what direction is that moving? Since I know phi is an angle measured from the positive z-axis, if I move in the direction of phi, it's going to produce, I'm going to make it long just so I can see what's happening. You know, r sub u is going to be pointing in that direction. And then for v is the theta, right? So as I move theta counterclockwise from the positive x-axis from that point, it's going to be pointing in this direction here. So this is what RV looks like. And according to the right-hand rule, if you can imagine this, curl your fingers hitting the red and then the blue, your thumb points outwards. And that's exactly what we wanted. We wanted it to point up or out, not down. So this parameterization is good as it is. I'm going to go ahead and now set up the flux integral. Okay, I computed the cross product here. You may have computed this several times now because parameterizing spheres is a pretty popular thing to do in this chapter. I used the sine squared v plus cosine squared v when I was computing the k component here. Okay, now I'm going to set up the integral. The vector field evaluated at the parameterization looks like this. And I dot that with u cross v. Okay, I certainly don't have the patience to compute this integral, although it's not really horrible. You can just use your rules for differentiating powers of sines and cosines to get it done, but I'll just go to Wolfram alpha. Okay, I'm just checking to see that I set it up correctly. For whatever reason, I did dv instead of dv du instead of du dv, but it doesn't matter. I'm integrating over a rectangle here. And apparently the answer boils down to 2 pi, a nice value of the integral. Let me go ahead and look at an image of this flux. So I'm going to graph the vector field as well as the surface here. So without the vector field, you can see that I've got my unit hemisphere here. And then when I add the vector field in, I can see that kind of overall I'm getting upward flow. Like if you just kind of inspect the arrows carefully, most of them are going up and to the left or the right or whatever. And I understand that, like, getting a positive value, 2 pi, for the flux of this vector field through the hemisphere when n is pointing up is measuring the total amount of flow from bottom to top. And since the flow appears to be going up through the surface, getting a positive number makes a lot of sense. Okay, let's move on to the next example then. So just another flux computation for practice. We've got a vector field given here, only has a k component, and then I want to parameterize this paraboloid in such a way that the normal vector points downwards. Okay, since the paraboloid is given as z is a function of x and y, we always have that cheap parameterization that just allows x and y to be the two parameters, and then z depends on those parameters as the function tells you to do. Now, we can look ahead because we want the end pointing downward. If we make x equal the u parameter and y equal the v parameter, then the r sub u is going to be pointing in the direction of the x-axis, and the r sub v is going to be pointing in the direction of the y-axis. And the right-hand rule will put that cross product, ru cross rv, pointing upwards. So since I want n pointing downwards, I'm just going to switch that up. I'm going to make x the v parameter instead, and y the u parameter, and that will reverse everything. And then for the parameter space, I want to see what, since my parameters u and v are coinciding with x and y, I want to see what region in the xy plane, which is the same as uv plane, that I'm going to range the parameters over. And if you see here, the paraboloid is cut off at z equals 5. So if you take the paraboloid 1 plus x squared plus y squared equals 5, then you can see that the circle I'm looking at in the xy plane is a circle of radius 2. So I'll bound my parameters appropriately once I get to the point where I need to integrate. All right, let me go ahead and construct ru cross rv. Okay, so take a look at this ru cross rv. This is supposed to be, an unnormalized, what do I want to say? It's not a unit vector, but it definitely is normal to the surface in the direction of the end that I want. So the fact that it's got a negative k component here makes me think that it's definitely pointing down instead of up like I wanted. Okay, so let me go ahead and then set up the flux integral. Let me call this region D for a second, because I'm not like really convinced that having u and v be the parameters is the nicest thing, because I'm integrating over a circular domain rather than a rectangular one. But anyway, bear with me for a second. So the vector field is 0, 0, x squared. Once I evaluate that vector field at the parameterization, I get this, and I'm supposed to dot this with ru cross rv. So this is what I'm saying. I need to compute this double integral. The integrand is just negative v squared. And I'm thinking of this region as being in the uv plane, right? So I'm looking at a circle of radius 2 in the uv plane, and I want to integrate negative v squared over this thing. Well, polar coordinates makes a lot more sense to do that, right? I mean, I can describe this circle using the polar coordinates, and I know how to convert from uv over to polar, right? I mean, it's the same way I would convert xy over to polar. So I think that's what I'm going to do here. I'm going to say, let's let u equal r cos theta and v equal r sine theta. And let's express this circle in r and theta instead, and then convert the integrand appropriately using v, and then I'll remember my r d theta when I convert the integral. Okay, and as usual, I might pop over to Wolfram Alpha to crank this out. So we're getting a flux of negative 4 pi when this is computed. Let me just check to see if the integral is set up appropriately. Looks okay. I'm using t instead of theta in Wolfram Alpha. Wolfram Alpha sometimes gets cranky with Greek letters. And why don't we go and graph the field and the surface and see if this negative answer is reasonable. So here is the image of the surface together with the vector field, and the vector field is clearly moving upwards, right? I could have told you that just by looking at the form of it. 0, 0, x squared means it always has this positive z value. And this surface, remember, we parameterized it in such a way that it was oriented downwards, right? So the amount of flux going down through the surface is negative.